of class. Okay, so this lecture we're going to talk about radiation. So another method of heat transfer from one place to another. And so the idea is any object is constantly emitting radiation. So we have some random object here, and it is emitting radiation. Which is carrying away energy. Now, what actually is this radiation? And it's basically light. Although we're going to see later that light in physics doesn't always mean what it does in like everyday use. You think light, you turn on the light, you can see things. However, light is a form of electromagnetic radiation. So let's just say it's emitting electromagnetic radiation. Now again, we haven't talked about electric. So again, electro and magnetic. It deals with electric and magnetic fields, which we have not talked about yet. So the basic idea, though, we have these oscillating electric and magnetic fields. And basically we're going to say that's what light basically is. Gets a little more complicated than that, but basically we're going to treat light as a form of electromagnetic radiation. And let's just look at, say, the electric field. Say you could take a picture, say you have a beam of light moving to the right. And say you could take a picture of it at one moment in time. And just look at the electric field. It might look like this. So we have an electric field that looks like this, and the whole wave is moving to the right. Okay, so just like one ray of light. So again, this is the electric field. So again, if you're standing there and looking at this beam of light goes by, like here the electric field points down, and then it points up, and then you're going to see like these waves as they pass you. So you're going to see the electric field oscillating up and down. And we call, like here we have like a peak wavelength, or peak electric field. Here's a peak electric field. We say the distance from one peak to the next is the wavelength. So we use this Greek letter lambda for wavelength. Okay, now electromagnetic radiation can have an enormous range of wavelengths. You could have things, well, like visible light is typically measured in nanometers. Several hundred nanometers, but still, very, very short wavelength. Whereas on the other extreme, you can go up to like meters. You can have electromagnetic radiation with a wavelength of meters. So it's got this enormous range, and we call that the electromagnetic spectrum. I'm going to actually draw the electromagnetic spectrum a little bit. So let's say we go look in terms of increased wavelength. So at the upper end, we're in the kind of the meter range. We have radio waves. And then if we, decrease the wavelength, we'll get to infrared. And then we've got, I'll just say V. I'll just say V for visible light. And then we have ultraviolet. Oh, I forgot one. Let me move everything over. So I guess between here, like radio waves, and we go with microwaves, this is what you'd have in your oven, and then infrared. And then visible And then I'm just going to call it UV because I'm running out of room. This is ultraviolet. And then below that, we have like X-rays and gamma rays. So this is basically the electromagnetic spectrum, and it's all electromagnetic radiation. They just have different wavelengths. So like over here we have radio waves. Over here we're looking at the visible spectrum. Again, these numbers are a little bit questionable because different people, see different things. So, but around 380 to 750 nanometers. That is the like visible light. That's what our eyes can see. And again, it does depend on the individual a bit. So maybe if you're exposed to 380 nanometer radiation, maybe you won't see it. But or 750, but maybe some people will, some won't. And then we get to very short wavelength, ultraviolet, X-rays, gamma rays. And I said light is electromagnetic radiation. It's a wave. Now, I also mentioned it's not quite that simple because turns out light is more complicated than just a wave. I'm not getting into too much detail now, but there was a very long dispute lasting hundreds of years. Or, scientists debated this for hundreds of years, like what actually is light. Isaac Newton said it was a particle. And then there's a guy named Thomas Young who said it's a wave. And around the kind of mid to late 1800s, more like the late 1800s, it became very firmly established that light is an electromagnetic wave. So it's not a particle, it's a wave. They even said, that's it, we resolved this, it's over. And that only lasted 10 years. And then Einstein came along and said, actually, light's kind of a particle and a wave at the same time. But we're mostly going to treat it as a wave. So again, it's not really a wave or a particle, it's its own thing, but it depends on the wavelength. When you have a very long wavelength, it acts just like a wave. When you get to these extremely short wavelengths, it kind of acts more like a particle than a wave. But in general, it has properties of both. But for most of the radiation we encounter, we can just say it's a wave and leave it at that. And we distinguish it by wavelength. And so here, this is visible light. This is what we see. And it's actually a very tiny sliver of what's actually out there. Like the entire electromagnetic spectrum. We just see a tiny portion of it. And there's nothing really special about the portion that we see. Just that's what our eyes can detect. So like if you go to like visible to infrared, it's just slightly different wavelength. That's the only difference. Now, different animals have different ranges as well. Some animals, I think like reptiles, can see infrared. And, why can't humans see it? Well, I'll actually get to that in a minute. Okay, so this is the electromagnetic spectrum. And everything is constantly emitting electromagnetic radiation. Like you are emitting electromagnetic radiation right now. Now, why don't we see that? Like if the room's dark and there's people in there, you don't see them even though they're emitting radiation. Well, it's just outside the visible spectrum. So to get an idea of what radiation would look like from an object, I'm going to draw this picture. Maybe it would be better if I held it up. So I'm going to draw it. This picture, this is the electromagnetic spectrum for different objects at different temperatures. And so a couple things to notice. Well, I might as well draw it as well. What we're looking at, on the horizontal scale, we're looking at the wavelength of the light, and then we're looking at the intensity at that wavelength. And so at like 3,000 Kelvin. So this is actually extremely hot. We had something like this. And then at a higher temperature, 4,000 Kelvin. Actually, I'm going to redraw this 3,000 one, just to make it maybe exaggerated a little. So this one was 3,000 Kelvin. This one is 4,000 Kelvin. And then one more, there's like 5,000 Kelvin. And like the area underneath this curve would give you like the total amount of, like the total power radiated by this object. And so like these higher curves, these are like the hotter the object, the more energy it's radiating. Now I should point out, for a real object, it's not going to look exactly like this. This is what we call an ideal black body. We'll talk more about that in a minute. But yeah, it's considered as like an ideal object. It's going to look something like this, where the higher the curve, like this one has the most area, it's emitting the most radiation. So the higher the temperature, the more radiation emitted. But you look at the peak as well. When the temperature increases, this is like the peak wavelength. Like this object at 3,000 Kelvin is emitting most of its radiation around this particular wavelength. For 3,000 Kelvin, that would be around like 600 nanometers, say. And as temperature increases, the peak wavelength decreases. So, yeah, peak wavelength, you see like at 3,000 it's emitting at that. 4,000 it's emitting at a lower wavelength. The peak is emitting at a lower wavelength. 5,000 lower still. There's actually a relation where the peak wavelength times the temperature is equal to this particular value, 2.998 times 10 to the minus third power meters times Kelvin. Again, you don't need to really know that number, but it's there. There's a relation between temperature and peak wavelength. And so again, these are very hot objects, 3,000 Kelvin. You know, that's almost the same as 3,000 Celsius. You know, when your numbers are this high, the offset of 273 isn't going to make too much of a difference. So again, we're talking extremely hot objects. And so if we decrease the temperature, we're shifting the wavelength to the right, to longer wavelengths. And so if you look at here, 600 nanometers, that's kind of getting to close to this limit of visible light. And so if we decrease the temperature, we're going to quickly run out of this visible light range. And that's why objects at room temperature do not glow visibly. They are glowing, they are emitting radiation, and it just peaks in the infrared part of the spectrum. And so that's why you can't see things in the dark. Even though what you see is mostly reflected light. Like in this room, I have lights on, and so light is bouncing off things, and you know that light bouncing around your room enters your eye. You're seeing light reflecting off of things. You're not seeing the light coming from things unless you happen to be looking directly at a light bulb. Or if you're outside and you look at a star or the sun, not supposed to do too much of that. So yeah, most of the light we see is just reflected off things. So it comes from a very hot source, and then the light reflects off things. That's what we're looking at. And yeah, kind of like you might think there'd be a huge survival advantage being able to see infrared, because that's what most of the things we experience radiate at. And so we'd be able to kind of see in the dark. And some animals can, like snakes or reptiles. And I think the answer why they can and we can't is because they're cold-blooded. And so they're not emitting, like they're the same temperature as the surroundings, so they're not emitting radiation that would kind of like mix in with the background. So like you're at a higher temperature than the surroundings most of the time, so like your body is emitting radiation, including your eyeballs, which your retina would pick up, and then would kind of swamp out any external source. So I don't think warm-blooded creatures could evolve to see infrared, but I know snakes can, and I think that's just because they're cold-blooded. So I've kind of wondered for a while why we didn't evolve to see that. And I think that's the answer. And again, other things can see ultraviolet light. Like I think bees can see ultraviolet. Oh yeah, so the visible spectrum, you know, like Isaac Newton is the one that came up with the colors of the rainbow. Red, orange, yellow, green, blue, indigo, and violet. So like infrared, that's like beyond red, and ultraviolet is, you know, beyond violet on the other extreme. So like out of the light we can see red is the longest wavelength and violet is the shortest. And it turns out the shorter wavelength stuff is more energetic. You can think of photons. It's kind of a more modern picture of how light works, where you can think of it as like a particle of light that has a wavelength, and the energy of a photon is proportional to its wavelength. Or, I'm sorry, it's inversely proportional to the wavelength. So if you look at red light, that's a long wavelength, the light isn't as energetic. And on the other extreme, if you look at violet light, that's a shorter wavelength, so more energetic. And again, when you get into ultraviolet, the photons of ultraviolet light can actually be energetic enough to be harmful, especially to your eyes. That's why you wear sunglasses that filter out ultraviolet light, so it doesn't damage your retina. It can also damage your skin. It can burn you because those photons carry a lot of energy. And then you go down to X-rays, very energetic, extremely useful in medicine, but you definitely want to limit your exposure to X-rays. And then you get to gamma rays. These are like the most energetic kind of electromagnetic radiation. You definitely want to avoid your exposure to that kind of thing. Okay, so basics about light, and everything radiates energy. And I think, like, say you have a dark room with like a metal bar inside, like a metal rod, or like a metal wire. And you're looking through a window and it's dark, you don't see anything. And so you run a current through that wire. And what happens when you run a current through the wires? It heats up. And so eventually, you keep increasing the current. Eventually it's going to become hot enough and it's going to start glowing red. Because, it starts glowing red. That's the, remember the, we're starting over here at room temperature, and as we increase the temperature, the wavelength shifts. And so again, it was glowing the whole time, but you only see it when it starts glowing red. And then if you increase the temperature, it'll kind of go through the spectrum. Now it's not going to shift from red to orange to yellow. It's not going to change color so much. Because this here we're talking about just like the peak, but it's emitting radiation in all the wavelengths around it. And actually you do emit some visible light. I think it's like maybe a couple photons a day of actual visible light. So you can never actually see a human being just by their emitted light, because it takes at least 7 photons to have any effect. Like your retina has to absorb at least 7 photons to have any effect at all. It won't notice anything less than that. And again, that wouldn't carry much information anyways. But it is kind of interesting that eventually, occasionally you do emit actual visible light. So again, if you look at an object glowing at, 3000 Kelvin, it's emitting light in all parts of the spectrum. It's just going to peak somewhere around orange or yellow because that's its peak wavelength. I actually have something in the notes with these kind of color ranges where violet is 380 to 420 nanometers. Yeah, so like orange is 590 to 630. So if we're at 3000 Kelvin, it's going to peak in the orange, but it's still going to emit significant red, yellow, green light, just kind of less green, blue, and so on. But it's going to emit all these colors, so it's not going to just change color from like one to the next. But yeah, I mean, the color that it's glowing gives you an idea of the temperature of the object, and that's extremely important in astronomy because we can look at the color of an object. In particular, this is a very important relation in astronomy because if we look at the light from a star and separate it into its wavelengths, we can kind of see where the peak wavelength is and use that to determine the temperature of the star. So, yeah, it's very important in astronomy in particular. But, yes, that's kind of the basics. A little bit about the electromagnetic spectrum and this radiation. Now, I say this is radiation from a perfect black body. Now, what does that mean? Like, what is a perfect black body? And the thing is, like, normal things, like here, this is a real object. And when you're looking at this, it looks white to you. And that's because what you're seeing is light reflecting off of it. So it's giving off its own radiation, but it's also reflecting light. And so, by definition, a perfect black body is something that would absorb all the light that hits it. And so it's not reflecting anything, and all you're seeing is this, what it's emitting, which would look like this. So real objects don't look perfectly like this because a perfect black body does not exist except for maybe like a black hole or something. Yeah, so that might be pretty close to a perfect black body, but yeah, normal objects, they also absorb some light and reflect other radiation that's incident upon it. All right. So yeah, this is that spectrum for a perfect black body. Now, we want to know, like, how much energy overall is going to be radiated by this object. So I'm going to erase everything here. So the rate that energy is being emitted from an object, I'm just going to write it down and then discuss each part. Okay, so E is called the emissivity. And this is a number, a pure number with no units. It's between 0 and 1. Now, 1 would be a perfect black body. Okay, so that's what E is. Now, something that's far from a perfect black body, like say a metal or something shiny, or maybe something like, well, no, it's mostly reflected light, but something that absorbs or reflects a lot of the light, yeah, that would be closer to 0. So something like charcoal would be over near the, like 1, or something shiny would be closer to 0, like maybe aluminum. So just an idea. Now again, this is a bit of an oversimplification. We're looking at this overall, like an object. This E would be kind of like an average value for the object overall, because different objects might absorb different wavelengths of light differently. So again, this is kind of a simplification, but we can take this as just for any object. It will depend on the wavelength the light that's hitting it, but this is good enough for us. Now the sigma, this is called the Stefan Boltzmann constant. We'll learn more about Boltzmann later. He was one of the leading scientists of his time in the 1800s. and we use this Greek letter sigma. And this is a fundamental constant. So it is, numerically 5.67 times 10 to the minus 8. That'd be watts per meter squared Kelvin to the fourth. So that's seen as kind of like a fundamental constant. Now, A is the total surface area of the object. So when I talked about conduction, we're looking at that, conduction energy is flowing in a direction, that area that showed up. And that formula is that cross-section area. Here, we're talking about the total surface area of an object. And, okay, so just have to know which area to use. Now, T is the absolute temperature. I'm going to underline that. Again, this has to be measured in Kelvin, or I guess you could use some like Fahrenheit equivalent of the Kelvin scale, as long as it's based on absolute zero. So again, an object that was at absolute zero would not radiate anything. Now, it turns out there's nothing in the universe that's at absolute zero. Even the empty space actually is not at absolute zero. It's a couple Kelvin. So like just normal background space is a few Kelvin. So T, it has to be based on the this absolute scale. If it was based, if you plug in T in Celsius, you could have like 0 Celsius. You'd have an object that's not emitting radiation at all, and that makes no sense. Okay, now I'm going to try to do one example right now, and then kind of take a break because my computer is running out of power and I'm going to have to recharge it. So I think I'll break this one up into 2 videos. But I'm going to try to fit in one problem right now. I'll rewrite our equation over here. Okay, so I've got this problem I really like. The star Betelgeuse has a temperature of 3,500 Kelvin. It's actually a pretty low temperature for a star. And that's because Betelgeuse is a giant, it's enormous. And it radiates energy at the rate, so its power, that's 4.61. I need to clean this board, but times 10 to the 31st power watts. Now this is kind of an average value. All stars are variable in their output. Like our sun, it goes through these sunspot cycles, so yeah, I mean the total output does vary up and down a bit. Betelgeuse is more of a variable than our sun, but again, pretty good value, like an average value here. And again, how would we know something like this? Well, we know how far away Betelgeuse is, and we can kind of look at how bright it is, and based on its distance, we can determine the rate that it's radiating energy. And again, how do we know the temperature of Betelgeuse? Well, again, we look at the light from it. Or we look at like the intensity at every wavelength. And it forms this picture that looks something like this. Now again, the real picture, there'd be like these gaps, which are actually important, but we don't need to get into that. But anyways, it looks like this, and again, you look at this peak temperature, and that kind of tells you, or the peak wavelength, that tells you the temperature of the star. So these are things we can determine just here on Earth from observing the light. Now we want to assume that Betelgeuse is a perfect black body, and find its radius. So let's start with the basic equation. We have E, which is 1. I'm going to write it down now, but then... okay. Now, what about the area for our Betelgeuse? So here's Betelgeuse. What is the surface area? Now, when I ask this in class, a lot of times I get pi r squared, because when you draw a sphere, it looks like a flat circle, which would have an area pi r squared, but the surface area of a sphere is 4 pi r squared. Okay, so we know the power, we know E, we know sigma, we know pi, so basically we know T, so basically we can just plug this in and solve for R. So it's a pretty straightforward problem, and it's just kind of interesting. Now I'm going to drop off this E because that's 1. So I'll put the 4 pi in front since that's a constant. So let's solve for R squared, and then we'll take the square root. So R squared would be P over 4 pi sigma T to the 4th. So we're going to plug all this in and then take the square root. So let's do this. Power is 4.61 watts. Now let's just divide by 4 pi. Sigma is 5.67. Now it's times 10 to the minus 8th, so I'm going to put that up on top. Units, and then it's over meters squared Kelvin to the 4th. I'm going to put that there. And then we divide by T to the 4th. So again, T is in Kelvin. So we don't have to convert it. We always want to check though. Okay. And let's check our units here. Watts cancels. Kelvin's going to cancel. So we'll get our radius squared in meters squared. Let's clean this up a little bit. Now 4 pi, that's around 12.56. This is 5.67. And then 3,500 to the 4th. We'll just... Okay. Now, because I'm running out of battery and I already have the answer, basically we would just do this and take the square root. So the radius is about 6.56 times 10 to the 11th meters. Okay, that's how big Betelgeuse is. Again, you can see this very easily, especially, well, not especially, but pretty much only in winter. It's in the constellation Orion. And, yeah, it's one of the brighter stars. So again, this is the radius of Betelgeuse. It's a huge number. Well, it's a star. You expect it to be huge. But again, numbers are only meaningful when you compare them to something. So I'm going to write down another number. It's around 1.5 times 10 to the 11th meters. Now, what is this number I wrote down here? This is the orbital radius of the Earth. So basically, if we look at, say, here's the Sun, here's Earth, so we're orbiting, oh, I erased the radius of Betelgeuse. That was 6.6 times 10 to the 11th meters. So if we replace the Sun with Betelgeuse, we would be inside Betelgeuse. This star is really enormous. It would if we multiply this by 4, that would give us 6, we'd still be inside. So that's Earth's radius. Betelgeuse would be something like this. So the Sun is this tiny dot here. Betelgeuse is bigger than this entire board, basically. So this star is absolutely enormous in volume. If you look at the mass of Betelgeuse compared to the Sun, it's still a lot bigger, but not nearly by this much. And don't forget, it's a gas giant. It's a very diffuse star. It's not nearly as dense. But, just the size of it, it is really enormous. So, again, there's a lot more to say about black body radiation, but my computer is going to die any second now. So I'm going to stop here and then just have a second video on this. We'll have a part 2. So that'll be it for now.